Two-dimensional dynamics is analyzing forces and Newton's second law when the forces are directed in both the x and the y plane. And the key component to remember is that perpendicular vectors are independent. So if we analyze, for our purposes right now, a frame of reference where up would be positive y and right would be positive x. The key to understanding two-dimensional dynamics and isolating is to separate the vectors into both the x and the y plane. And so this is very similar to the analysis we had for two-dimensional kinematics or projectiles, which is analyzing both the x and the y direction, finding the forces that are appropriate in both individual directions, isolating them as separate, and then trying to figure out what links the two sides together, what commonalities they may have. There are many examples of isolating these things, and some of which we've already talked briefly about. For example, thinking about a lawnmower sitting on the ground. A lawnmower has a long handle directed down like this. Whenever we analyze for the forces on the lawnmower, it's true that they are pushing, the operator is pushing down along the handle in this direction. So the force along the handle is both in the y direction, Fy, and in the x direction, Fx. But don't simply stop there. Recognize that the forces that we've seen already in one dimension still exist. So there will be f of g in the vertical plane, and then as a result of sitting on the ground, there would also be a normal force pushing up, which is the function of the ground pushing up on the lawnmower in this direction. So when we analyze the forces, it's important to note that everything in the vertical plane would be analyzed according to Newton's second law, equal to m times a in the y direction, and anything in the horizontal plane would be analyzed separately in the x plane, equal to m times a in the x direction. The link between these two can often be a force that is common to each, or in some cases, a interaction that is common to each. And we'll be looking at a number of examples, but it's really just a matter of separating the vectors into the two perpendicular components and then analyzing them individually and drawing conclusions about that information afterwards. As we saw with velocity when we were doing projectiles, this force that's along the handle here, F, will simply be used to calculate Fy and Fx based on an internal angle within the system. After you've utilized this F, it doesn't get put into the sum in the y or the sum in the x direction because it points neither y or x directional, right? And so after you use this to calculate Fy and Fx, leave it alone, right? Just leave it in your diagram because it wouldn't be listed in your horizontal or your vertical forces, right? The most common examples for introducing and analyzing two-dimensional dynamics will be problems of balance and pulling and pushing in various two-dimensional planes. And the example that I think of is a high wire walker connected between two high cliffs. So if we have a person walking across a high wire that stretches down and then up attached like this, we know that the tension within the system, F of t, is going to be directed along the rope this way and along the rope this way. And that tension force is a set value that it's the same in both directions, right? But neither of those tension forces point in the xy plane. And so it's very important to recognize that this side of the triangle can be written as a force going this way, F of t in the x direction, and a force going this way, F of t in the y direction. And if the problem is symmetrical, then it would make sense that those same forces would exist on this side with Ft in the x direction and Ft in the y direction on this side of the triangle as well. we know that in a state where this object, the person's balancing on the high wire, is at a constant velocity and or a state of rest, then we know that all the forces are balanced, right? Which means that the summation of the horizontal forces is 0, which means that these two things cancel out. And the summation of the vertical forces is 0. Well, this is curious because here we have two f of ty's pushing solely up. And so the explanation of what that's canceling out has been overlooked in the sense that f of g acts on the object going down in a vertical way. And so this gravitational force is a vertical force that would be listed along with these two f of ty's. And so the summation of f of t plus f of ty plus f of g is equal to 0, whereas here these two are simply the only horizontal forces. So we'll use an angle, an internal angle, in order to recognize that we can turn f of t into f of tx and f of ty. By symmetry, we would expect this side to be the same, and then we just generate our sum of the forces in the y direction, our sum of forces in the x direction, and analyze for whatever's being discussed. Again, we're using the hypotenuse force to determine the component forces in the x and the y direction, and then abandoning it because it doesn't match our frame of reference. Some further examples that we'll get into a little bit later have to do with when the actual surface is in a new and interesting direction. And so if we have something like an incline with a ball either rolling up or rolling down or doing some action on the hill, we know that generally, right, we have f of g as an always vertical force. F of g is down. But what we see is that this contact force with the surface pushes us out from the surface like this. This is called the normal force. This would be the force due to the incline. And again, the issue is that this normal force does not match a vertical or horizontal frame of reference, which means that as it sits, this should be analyzed as both a force pushing forward in the x direction and a force acting upward. Okay? So this would be f of n in the x direction, and this would be f of n in the y direction. And so there we see that f of n in the y direction and f of g are the actual opposition forces. And oftentimes it would make sense that this f of ny is not exactly the same as this, which is why the ball ends up going down while also being pulled over, right, along the horizontal. And what we're going to discuss a little bit further in a later video is how we can actually rotate the frame of reference in order to generate perpendicular vectors into a new and interesting frame. That will come later.